Alright, so welcome back to Chapter 6. And in Chapter 6, we're going to be talking about a sampling distribution using estimators. Alright, so a sampling distribution is this item that we're going to look at. It's very, very similar to this continuous normal probability distribution. The only difference here is that we start looking at all of the different samples that we actually get within our distribution. And looking at these samples, we then want to identify what is the mean, what is the standard deviation of all of these possible samples, and then can we extract something useful. Alright, so this example. Given 3 numbered pool balls, we will select 2 of them with replacement. So again, with replacement means that if we choose ball number 1, we can put it back and we can choose it again. And we want to find the mean of those numbers. So as soon as we choose those 2 balls, we're then going to take the average or the mean of those numbered balls. Alright, so here we go. We're going to pretend that we're going to put these pool balls inside of a bag and we're going to choose them at random. Alright, so ball number 1 that we choose will be the one that's numbered number 1. Well, we're going to put it back in. When we put it back in, what's the next possibility? So choosing ball number 2, we once again can run through getting ball number 1. Alright, now if ball number 1 was again the one that's numbered 1, then the next possibility is that we don't choose the number 1 again. Now we can choose the number 2. Well, what if we did choose ball 1? What's the last possibility possible? Well, that's going to be ball number 3. Well, the fourth outcome, now that we have all of the different combinations when we chose ball number 1 first, let's look at all the different combinations if we would have chosen ball number 2 first. If we choose ball number 2 first, well then, the second ball could be ball number 1, or the second ball could be ball number 2, or the second ball could be ball number 3. Now moving to the next outcomes. The last 3 balls, I could choose ball number 3. That means my second ball would be ball number 1. Ball number 3 was chosen first, so then ball number 2 can come second, and then ball number 3 can be chosen again. And what we want to do is we want to find now the mean between these numbers. So what is the mean of 1 and 1? In other words, what is the average for 1 and 1? Well, that's just 1. What's the average, or what's the mean for 1 and 2? Well, that's 1.5. What's the average for 1 and 3? That's going to be 2. What's the average for 2 and 1? That's 1.5. What's the average for 2 and 2? That's 2. What's the average for 2 and 3? 2.5. Excuse me there. That's 2.5. What's the average for 1 and 3? That's 2. The average for 3 and 2? That's 2.5. And the average for 3 and 3? That's 3. Nice. So what I'm going to do now is I'm going to take all of these averages, all of these means right in here, and I'm going to rewrite them down here. Alright, so again, I'm just taking those and I'm writing them down. I see the mean of 1. So that's there. I see a mean of 1.5. That's there. I see a mean of 2. I see a mean of 2.5. And I see a mean of 3. And again, all I'm doing is I'm writing all of these means down without repetition. And the reason I'm doing that is because this is kind of now like my sample space. So as I'm looking at this sample space, I now want to jot down that frequency. How many times did the number 1 appear for all of those means? Well, that number 1 as a mean only appeared 1 time. How many times did 1.5 appear as the mean? That was 2 times. How many times did the mean of 2 appear on this list? That was 3 times. How many times did 2.5 appear on there? That was 2. And the number 3 as the mean only appeared once. So now I want relative frequency. Remember, relative frequency is just going to be the frequency divided by the total sum. So what's this total sum? In other words, how many samples did we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. It's the same as if we would add all these frequencies. So that's 3, 3, and 3, that's 9. So that's just 1, 9. So as the relative frequency, all I'm going to do is get a decimal for that and type it in for the relative frequency, which is 0.11. Nice. Next frequency was 2, so that was 2 out of 9. So when we do 2 out of 9, again, all I'm looking for is just the decimal version for this, which is 0.22. The next one, 3/9. That's 1/3. That's 0.33. And then after this, they just repeat again. There we are. And what we want to do now, once we finish this relative frequency here, we want to actually graph that relative frequency. All right. Now, I'm going to display this with a bar graph. And the reason I'm going to display this with a bar graph is because all of my data here is discrete data. So looking at this discrete data, I'm going to jot this down as 1, 1.5, 2, 2.5, and finally 3. So the 1, relative frequency wise, had a relative frequency of 0.11. So that was 0.11. There we are. 1.5 had a relative frequency of 0.22. So there's 0.22. Relative frequency of, mean of 2 had a relative frequency of 0.33. And the other ones, again, they just did the same thing. 2.5 and then back to 3. There we are. So here's that relative frequency distribution reflected as a bar graph. And the reason we want to look at it this way is because of this. What does that kind of look like? What kind of distribution would you be able to describe it as? Would it be uniform? Would it be skewed? Or would it be symmetric? If you said symmetric, you're right. We're looking at a normal distribution or a Bell distribution or a symmetric distribution, which means whenever we're looking at these sampling distributions that we typically observe kind of fall under this normal distribution. So when we start looking at the mean of the means, okay, that's kind of rough to say. All right, the mean of the means, but that's what we want to look at. So on the sidebar over here, on the side of the page over here, what I'm going to do is I'm going to find an average. In other words, I'm going to find a mean for all of these values here. All right, and I'm going to see what I get. All right, so that's going to be a separate question for me, that I want to find the mean of the sampling means. What does that mean? Well, that's a lot of means. What does that imply? That implies that out of 1, 1.5, 2, 2.5, and 3, I want to find this mean. All right? So, looking at this, well, we have a frequency. So, because we have a frequency, we have to kind of keep that in mind. All right, so we kind of have to keep that in mind. So what we're going to do is we're going to use this sampling mean along with their frequency to see what we get. All right, so if you remember, in order to find this mean, what we typically do is we take the mean and we multiply by the relative frequency. Once we take that mean and we multiply by the relative frequency, that's then going to give us the mean for this probability distribution. And that's what we're going to do. But we're going to do this on the TI. All right? So, a different way to do this is just to take all of these means, add them all up, and divide by 9. That would be an easier way. Let's see if we can do that. All right. So here we go. We're going to take 1 by 1. So that's going to be 1. 1 times 1 plus 1.5 times 2 plus 2 times 3 plus 2.5 times 2 plus 3 times 1. All right. And we're going to divide all of this by 9 because there's 9 samples. All right, so the first one's just 2 times 1.5. That's going to be 3. That's 1 plus 3. 2 times 3, that's 6. 2.5 times 2, that should get us 5. And then finally 3 times 1 is just 3, divided by 9. All right, let's add all this up. So that's 6 plus 3 plus 1. That's going to be 10. That's 15. 15 plus 3, that's 18. So that's 18 divided by 9. 18 divided by 9 is 2. Nice. So what we get here is we were able to extract the mean for the sampling means. All right. Now I want to take a second really quick. And the reason I want to take a second is because what if we found the mean for the initial pool balls of 1, 2, and 3? So what is the mean of these pool balls? 3, 4, 5, 6. 6 divided by 3? 2. What do you see here? Is it just some random coincidence? Is this the world trying to tell us something? Or is Mr. Castro just being sneaky by referring to himself in the third person? I really hate referring to myself in the third person, but I have to sometimes. So, or am I just being sneaky to try to allow you guys to explore some topics? Decisions. Actually, this is no coincidence at all. This is no coincidence at all, and it's no coincidence because at the end of the day, what we want is we want to select what are known as these unbiased estimators. And you actually get to see that definition right down here for an unbiased estimator. Whoa, what's going on here? Whoa, ¿qué pasó? I don't know what happened. I try to be crafty here, but it's okay. Technical difficulties. I always have them, and it's okay. We got to just roll with the punches. All right, so here we go. Now, what we want is an unbiased estimator. Now, what does unbiased mean? Well, that means that you're not going to change your perspective. You're not going to change your outlook. You're not going to change your value given the fact that you're going through all of these different, let's say, changes, right? So, I want you to think about this, all right? Now, typically, whenever you go into, let's say, be a juror on a case, right? You're part of a jury. Typically, you want jurors to be unbiased. If they're biased, then they're going to vote one specific way, or they're going to lean towards one specific way. We want to make sure that the decisions are based off of logic, off of reason. And that's going to stand the same thing here when we're talking about these numbers. We want to make sure that these numbers don't change based on what's going on around them. Meaning, this mean initially was 2 for all of these numbered pool balls. Once we were able to take a lot of samples, took those samples and then took the mean of those samples, and then finally took the mean of those means of the sampling means, we then got the exact same value. Which means that estimator is unbiased. It didn't change. All right? these sampling estimators, we always want to make sure we extract. And there's a few of these sampling estimators that we work with that are unbiased. Number one being the mean. All right, my apologies, now I'm back. All right, so mean is one of our unbiased estimators. Proportion is another unbiased estimator. And the last unbiased estimator is variance. These values are unbiased estimators, which means we can use these to estimate facts or to estimate or to infer something about our population. So, mean, what does that look like? Well, that's your X bar. Proportion, we're going to talk about P hat. All right, that's P with a little hat. Yes, I know, it's kind of cute. Variance, sigma squared. These are all of the unbiased estimators that we want. Now, unfortunately, here at PCC, we don't cover the unbiased estimator for variance. We did at one point in time, but we don't now. But it's important still for us to know that that is one of the unbiased estimators that we can use. Now, what is a biased estimator? What is something that we don't want to focus on? The items that we don't want to focus on here is our standard deviation. Standard deviation is not, oops, wow, I cannot spell while I'm talking. Deviation. There we go. Standard deviation is not an unbiased estimator, so we have to be careful with that. That's actually a biased estimator. All right. So we have to be aware of this, and we have to know that when we're looking or when we're working with these sampling distributions, that we do have a certain way to deal with them. All right. Now, let's see, the next section is going to start in just a little bit. And we're going to talk about what all of this means when we're using these notations. So we're going to get into notation in just a little bit. All right. Now, before we get to that, I actually want to give you this here. Is equal to just the mean of the population. What this says is that this was the average of all of your samples, and this here was the mean of the population. This one here. Which means mean of the sampling means is equal to just the population mean. And that's what this guy gives us here. All right. So I'll leave you with that now. And again, that wraps up now section 6.3. There's not much to it. I won't really test you guys on section 6.3 besides the definitions and the concepts that we extracted from here. All right, the definitions and the concepts are going to be something that we keep using very much in our class moving forward. All right, so I hope you guys enjoyed section 6.3, and I'll see you next time.